Buffers. So buffers, you've probably seen buffers in different courses. The way that we form a buffer is by creating a solution of a weak acid and its conjugate base, so the HF and the F minus. Okay? And then we have two equilibria that are in play, right? And we'll talk about that. The purpose of a buffer is to resist change in pH. So often we want to perform a reaction at a particular pH, and a lot of the biochemistry people do is done it at a certain pH, and so they'll use buffers. The way it resists change in pH is by reacting with either an acid or base, if that's what's added, to neglect any major change that those would usually impose. It also keeps the pH fairly constant when there is a change in volume or a change in temperature. So buffers are really useful for sort of maintaining particular reaction conditions. So let's look at what happens when we make a solution of a weak acid HA and its conjugate base A minus. So we usually talk about adding the sodium salt of the conjugate base. Okay, so you might see Na, lowercase a. That's the sodium salt of the conjugate base. If we have those two substances and we put them in one beaker, all right, in that beaker we're going to have two equilibria, and they are related. We're going to have that of the weak acid, its equilibrium with water to form A minus and H3O plus. And we're going to have A minus that reacts with water to form HA and OH minus. So you can see that they are related because there's conjugate base on the reactant side for the first reaction, and it shows up in the second reaction on the reactant side, and conjugate acid on the product side of that second reaction. Excuse me. So if we upset one of the equilibria, the other can sort of come in and make account for some changes in the solution. So how does So let's take our HF and sodium fluoride example. We put that into solution. Let's say we add equal molar amounts of NaF and HF. Taking a look at these two equilibria, 1 and 2. If we add HCl to a beaker that contains both HF and NaF, so these two equilibria are happening. We add HCl, we form H+, okay? Does H+ react with, what does H+ react with? First, does it react with HF? Does it react with F minus? Nothing. Does it react with nothing? Does it react with OH minus? So if we add H+ to the solution, it will react with F- to form HF. Okay? So if we add an acid to a buffer, it's going to react with the base form of the buffer component, in this case F-. And you'll notice that it forms HF. Okay? This is where it gets a little bit complicated, so just listen, don't write it down. It doesn't matter all that much in this course what's going to happen next, so I just want you to listen. So if we form HF from this reaction, what happens with HF? This equilibrium. We reform more F-. So when we say that a buffer doesn't allow for dramatic changes in pH, It's because both of these equilibria are happening simultaneously. We reacted away some F minus when we added H plus and formed HF. But that HF dissociates a little bit to reform some of that F minus. So that's sort of the magic, quote unquote, of a buffer. But what I want you to really recognize is what a strong acid added to the buffer can react with, and if we add a strong base, what does it react with? And so in this example, OH minus would react with HF to form F minus and H2O. Okay? Questions on that? Okay. So again, here's another example where we have an acetic acid sodium acetate buffer. This is a really common one. It makes a buffer with an acidic pH. So the pink boxes show our weak acid, acetic acid HA, and the blue represents the conjugate base, A minus. Let's say we start in the middle with a buffer that contains equal moles of HA and A minus. We go to the right, we add OH minus. That OH minus is going to react with the HA. Right? We see a decrease in that acid concentration. HA goes down, just a little bit. And we see an increase in the conjugate base concentration. The opposite happens when we add H3O plus. We see an increase in the HA concentration, decrease in the conjugate base, and the reactions that are taking place are shown below. It's not showing that subsequent reaction to replace some of those initial substances. Okay, so this is a plot that it's kind of a different plot. You've maybe not seen one like this before. This is a plot where we have pH on our y-axis, just like a titration curve. On our x-axis, we have moles of base added, it goes to the right, and moles of moles of H3O plus hydronium ion added, it goes to the left. Okay? So 0 is in the middle here. No moles of anything added. That's the initial pH of a buffer. So we're going to say we have a buffer solution. The initial pH is somewhere just above 4, between 4 and 5. Okay. If we add moles of hydroxide to this buffer, we see an increase in pH, but it doesn't increase very dramatically. All right, that looks here. That looks like this. If we add some moles of H3O plus, we see a slow decrease. Okay. You may have seen a plot that is, this is a zoomed in portion essentially of a titration curve. Okay, the beginning part of the titration curve. As long as we have a weak acid, but we'll get there. So what if we instead, for comparison, did this for a solution that was nothing. We have water in a beaker, okay? Instead of a buffer. So this is for a buffer. What if we just have water and we add a half mole of OH minus and a half mole of H3O plus? Okay, let's think about what happens to the pH. Think about in your own experience, you have some water, you add strong acid to it. What happens to the pH? It decreases very quickly, right? And so what we end up seeing is something more like this. Let's draw it in red. pH decreases very quickly. If we take a beaker of water and we add strong acid to it, the pH increases very quickly. Okay. Eventually we reach a plateau because we can't add any more. Right? That's where that's coming from. The main idea here is that a buffer resists change in pH because there's a reaction taking place. It doesn't allow for drastic changes in pH, unlike in pure water. Okay. Does that make sense? Kind of. There are ways to determine how well a buffer works, and we talk about buffer capacity. We're not going to do any calculations of this, but what it comes down to is the best buffer has a pH close to the pKa for its acid, and the concentration of acid to base are between 1 to 10 and 10 to 1. So basically, the best is when you have equal concentrations of HA and A minus in solution. We want our pKa to be close to the desired pH. Okay. And so the question here is, if more base is present in the buffer solution, is the buffer more resistant to acid or base? It would be more resistant to acid because there's more base to react with that acid. So that's just sort of where we're thinking with buffer capacity. Okay. But I'm going to go to the next bit here. Calculating the pH of a buffer. You actually have all the tools that you need at this point in order to be able to calculate the pH of a buffer. Right? It's essentially just equilibrium, ice tables. So what we could do, let's say we have an acetic acid, sodium acetate buffer. We could write out that equilibrium shown here. We can make an ice table. We would have initial concentrations of both acetic acid HA and A minus. Okay. We would have two initial concentrations. We would figure out how that reaction proceeds, and then write an equilibrium constant expression and calculate it that way. But there's an easier way. So I will just show you the easier way, and I will skip the hard way. The easier way to calculate the pH of a buffer, and only a buffer, is through the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation is simply a way of someone took an Ka expression and rearranged it to give you this. And then they got their name on it. Okay? That's how amazing it is. But you can only use it for buffers. Do not try to use this for weak acids or weak bases by themselves. In this equation, we have pH equals pKa plus log of the conjugate base concentration over the acid concentration. Okay? We typically use concentrations in here, and you need to know the pKa. Inevitably, you will look up Henderson-Hasselbalch equation on Google, and you will see one with pKb and maybe a different sign, and maybe flipped HA and A minus. Okay? This is the one you're going to get on the exam, so I would practice your problems with this equation. It's the one I have memorized. If you want to remember this, pH equals pKa plus log of, aha, there you go, aha. Yeah, it's really good. Okay, let's quickly do one problem. We're going to take 100 milliliters of 1 molar acetic acid, and 100 milliliters of 2 molar sodium acetate, and we want to calculate the pH of the buffer. We have the Ka. From that, we can take minus the log of the Ka to get the pKa. It is 4.77. Okay. We need concentrations, all right? So we have to figure out concentrations of HA, or acetic acid, and for the sodium acetate. For the acetic acid concentration, we know we have 100 milliliters of 1 molar acetic acid. We're combining that with 100 milliliters of 2 molar sodium acetate. 2 moles per liter sodium acetate. So we have a total volume of 200 milliliters. Okay. With these buffer problems, pay attention to this total volume. Sometimes we'll give you the total volume. Sometimes we'll need to add it up. So just kind of watch that. So to calculate the concentration of HA with a new total volume, we need to use the dilution equation. If you recall, the dilution equation is M1V1 equals M2V2, where M is molarity, V is volume in liters. You may also have seen C1, V1, C2, V2, something like that. Same thing. So to calculate for HA, we start with our M1 is 0.1 moles per liter. 1 mole per liter. Initial volume is 0.1 liters, or 100 milliliters. We're solving for M2, the new concentration at the new total volume, which is 0.2 liters. Uh-oh. What did I do? Oh, this again. Okay. So M2 then is equal to 0.5 moles per liter. And for A minus, concentration of A minus, we start with 100 milliliters or 0.1 liters of 2 mole per liter solution. And we dilute up to 0.2 liters. So M2 is 1 mole per liter. So now we have our HA concentration. We have our A minus concentration. We have pKa. And so we can solve for the pH. pH is going to be equal to 4.77 plus the log of A minus 1.00 divided by HA 0.5. And we're going to get 5.07. Okay. If you would have done an ICE table, you would have had to, figure out all the different parts that go into the ICE table, solve for X and all of that. Much easier.